awesome. But first, to get Simpson's rule, you have to understand trapezoids in a kind of different fashion. So let's think creatively, shall we? If you did the trapezoid here for the estimating the area under the curve with two trapezoids, then let's do it equally so you have one at 2 and one at 4, right? The trapezoids then would go this kind of path and this. And it says sketch the error. Where's the error in the estimate? Right? All right. Now, those trapezoids, do they overestimate or underestimate? Oh, because the curve is increasing? Because the curve is concave. All right, now let's look at this in a slightly different way. All righty. I think you'll agree that trapezoids are found by doing this. Okay? Now what I'd like you to consider is, isn't that the same as this? Isn't that the same as that? All right. So what do you make out of that? The trapezoid is like a... It's not the same. I took the H off to the side. It's totally different. What is this? Oh, what is this now? No. What?
Average base.
It's the average of the two. Okay, so this is the average base. Now remember, these bases run parallel. So this is the average y times the height. This is like a rectangle with some kind of average of the two parallels times a base. So let's think of this in a different way here. This height 1 was 0 and height 2 is roughly, I think these go by 5, so height 2 is roughly 10. So what's the average height in there? If the first height was 0, the second height was about 10, then the average is 5. I'm so proud of one of you. Okay? Oops, that's terrible, but that's okay. All right? Now, in terms of the error now, isn't that rectangle overestimating a lot? And over here, it's underestimating a little, but the net result is it's doing a lot of overestimating. Does that make sense with over there? It's supposed to be the same as that trapezoid, and that trapezoid definitely overestimates, yeah? So this net area should be the same as that blue error. Now let's go to the next here. This height was about 8 or 10 or whatever, and this is about, what is that, 60, 70? Okay, so what's average roughly of 10 and 70? 40. Okay? Jeez. This does not bode well for the high concept to come. All right, so there's a rectangle with a lot of overestimating area and a little bit of underestimating area. But the net result is way more overestimating, which also makes sense because we know that trapezoid did overestimate. You with me? Okay, now, the idea of being a quick trapezoid estimator is just average the two parallels is useful on a lot of problems. So, for example, on the homework, if you didn't do this problem on the homework, get it out now. Let's crank this one out. I think I changed it to 4 for you guys, yeah? Did I? Okay. So, rather than using that trapezoid rule, I'm going to do some quick averaging of the parallels. So this first is 2 wide, and what's the roughly average of the two parallels? If it's 0 to 2, then the average is The next goes from 4 to 6, so it's 2 wide. It looks like the heights go from roughly 2 to roughly 3. So the average is 2.5 or 5 halves. Are you with me? Okay. The next region from 6 to 8 is 2 wide, and if I average the heights, then I'm taking roughly 3 and roughly 4. So an average height of 3.5. And then the last region from 8 to 10, I'm taking a rough of 4 and 0, and the average is 2. So a good estimate is 2 plus 5 plus 7 plus 4, or 18. Hi. Oh, you're back. Okay. So if I counted those blocks, does it look like it's roughly 18? This is, I'll get your tuck here. Does it look like roughly 18 blocks? Count, go. Okay, moving on to Simpson's rule. Now that you practice trapezoids in a different way, let's talk about Simpson's rule. So, midpoint and trapezoid. They're the best estimation methods, better than left and right. So, move the above right trapezoid area with midpoint rectangles, which use, okay. So, if I were doing trapezoids and using 2 trapezoids, then by the trapezoid method, or the average y method, we said that the average y here is roughly here, and the average y here is, what's that, we said here, yeah? That's just the same as what we did before, right? Now, let's compare, and we said, actually, we'll come to that. Now, let's compare that to 2 midpoint rectangles. And this is good review because it's been a while since you did midpoint, I believe. So, when you do midpoint rectangles, instead of using an average y, you really go with an average x. Halfway in between 0 and 2, you look at 1, the average x, and you draw the height there. Now, isn't the height at 1 basically like that, yeah? All right. Is that gonna, well, maybe the next rectangle will tell us more. Between 2 and 4, where do we draw our height at? 3. So if I go to 3 and draw over and over, let's talk error there. It's a little closer in terms of area, yeah? But which, does it look like there's more underestimating error, area under the curve, or more area over the curve? I agree. It looks like under's a little greater. So overall, it seems like I'm getting a net underestimate there. We'll get into that. The curve is concave up. We talked yesterday about trapezoids and concavity. Do trapezoids over or underestimate the true area? This might help to go back to actual trapezoids instead of this average rectangle idea. Trapezoids overestimate. Now, the midpoint, it seems like we're getting a little bit of an underestimate when it's concave up. Now that's useful now because we have a fence on both sides rather than just one side. we can say the true area under the curve is between the two estimates. What's the lesser of the bunch, midpoint or trapezoid? We said midpoints underestimate, so they are the least, and trapezoids overestimate, so they are the most. Now that's only because it's concave up. If you look at a concave down curve, then here, when you take a midpoint rectangle, because the curves or the y values are decreasing, you're going to get more area on the left than the right. So concave down, midpoints overestimate. Generally speaking, you should probably get that in the note box here. If f is concave up on the interval, midpoints underestimate. And if the curve is concave down, midpoints overestimate. Now, I didn't give you the equation that we are dealing with, but now I'm telling you that's a cube graph on there with a scale that's kind of blown up for the y so we can get it on the graph. But if I ask you to find the two estimates, both midpoint and trapezoid, then the exact value, then let's go trapezoids, two trapezoids. If we're doing equal subdivisions, I can factor out. What factors out front of trapezoid estimates? I factor out the height, right? Do you agree? And what's the height? Which runs parallel. The delta x is 2. And what else do I factor out? The over 2. Why is that there again? Yeah, it's for the trapezoid formula. Base 1 plus base 2 times height divided by 2. We're factoring out that divided by 2 part of the formula. And the inside is f at 0. And then what about the next point? Where's the next point I come to? 2f at 2 is because it's part of a left trapezoid and a right trapezoid. And then ending at single f at 4. That's 1 times f at 0 is, we're talking the cube function now, so f at 0 is 0. 2f at 2, 16, and f at 4, 64. So I get a trapezoid estimate of 80. So when I go to find the true area, will it be more than 80 or less than 80? 80. Less. Remember, our trapezoids are overestimating. Yeah? So our true area when we go to find it should be less than 80. Let's go to midpoint. If I do equal subdivisions, then I can factor out, let's go 2 rectangles. Yeah? Midpoints are rectangles. And in this case, equal subdivisions mean I can factor out the base and just find the heights. What's the base of each rectangle? 2. And height 1 is f at, now we're using midpoint. So do I use 0, 1, or 2? F at 1, which is the midpoint between 0 and 2. And f at 3, which is the midpoint between 2 and 4. What is f at 1? And f at 3. 47. So my overall estimate is 56. Should that be more or less than the true estimate? Less. Right? So the true estimate should be between 56 and 80. Let's find the true area. How do I find the true area? Integrate from 0 to 4 of x cubed. 1/4 x to the 4th from 0 to 4. How does that come out? It is 64. It seems like that is what we were hoping for, something between 56 and 80, yeah? All right. What do you notice about the error, or the accuracy between the two? Which one's closer? Midpoint is more accurate. What's the error? That's true. The midpoint error is 8. And what's the trapezoid error? 16. So it seems like the midpoint, the midpoint, thank you. The midpoint is twice as accurate as the trapezoid. Well, that scared you. That's funny. Okay, so the midpoint is twice as accurate as the trapezoid. So logical would be to say, well, geez, if the true is between the two, then we should average the two. But if the midpoint's more accurate, should we just straight up average them, or what should we do? Don't we want to favor the midpoint if it's more accurate? So we should do I was looking for a little vocabulary. Double average is not a thing, although I assume what you're saying. It's called a weighted average. We're going to use a weighted average. That's Simpson's rule. It uses a weighted average, weighing midpoint more than trapezoid. Sorry, I blinked out for a second. Okay, so here we go. Simpson's rule uses two of the big ideas we just saw. The true integral value is between the two methods, so we could use both midpoint, which I'm going to abbreviate M, and trapezoids, which I'll abbreviate T, and that's pretty common at least in the 3 textbooks I looked at. Okay? The midpoint method, though, is generally twice as accurate, so we could use a weighted average. So our Simpson's rule estimate would be a weighted average. So we would take 2 midpoint estimates and add in a trapezoid estimate and divide by 2, 3. So weighted average, there really are 2 midpoints in a trapezoid. That's 3 altogether, so we divide by 3. You follow? All right, now let's take that a little further and make a little grand formula out of this. So we said S is, let's go 1/3 out front of 2M plus T. 1/3 out front. Now let's get into the 2M. The M, actually I'm going to need to go braces here. Okay, the M, when I did, what does M stand for again? Midpoint rectangle. When I did M, what did I factor up front? A base. Okay, and inside was height 1 and height 2, yeah? And the trapezoid, what did I factor up front? The height, really, over 2, and inside was F at 0 plus 2F at 2's plus F at 4's. I'm getting there. Right, small. I need a couple more lines. Probably need 3 more lines to get there. Are you okay so far? Okay. Let's go to base. Isn't the base just the delta x? Okay. All right. And H1, for the midpoint, what was the first height? F at 1. And the second height, F at 3. For the trapezoids, what's H again? Which, remember, runs parallel to the delta x over 2, and the rest of it's fine. Studying? Okay. Now then, let's do some cleanup. They both have a delta x. So, question is what to do about the 2's. Let's do this in 2 pieces. Let's pull out the delta x. And I have 2 F at 1's plus F at 3's. Okay, whatever. And 1/2 F at 0 plus 2 F at 2's plus an F at 4. Wait. All right, let's deal with the 2's. Do you want to factor a 2 out or a half? 2. Try again. All right, good call. If you factor out a half, then it becomes delta x over 6. Okay, cool? Delta x over 6. And, all right, so when I take out a half, what does this become? A 1 or a 4? 4. 4 f at 1 plus f at 3. And then just normal, no parentheses, f at 0, 2 f at 2's, and a single f at 4. Yay? Okie dokie. Almost there. Delta x over 6. Now, putting this in order then from least to greatest, f at 0 would come first, right? All right, and there's just one of those. What's the next thing we would come to? F at 1, and how many of those are there? 4 f at 1's. And then 2 f at 2's. And then 4 f at 3's. And finally, an f at 4. All right. Now, this is Simpson's rule. And delta x is a little different than what we're used to here in that is this helping you at all? Okay. Delta x is actually twice as many, where's this? So delta x is a little different because it's half as much as our delta x's. Do you agree that by mixing both trapezoids and rectangles, then instead of going by 2 in both, we're going 1, 2, 3, 4, so we're actually getting twice as many subdivisions in Simpsons as we did in the 2 before? Yeah? You with me? Are you with me? Okay, cool. So the delta's a little funky in here, but so delta is half as much of the midpoint and trapezoid delta. But we'll still find it the same way. So what I want you to understand then is why that delta is over 6. And the formula is really delta x over 3, where this 3 represents the weighted average idea. And why the over 6 really says, because we have twice as many subdivisions when we combine the 2. Now, don't worry about the delta. It'll be fine. The delta x over 3 and delta x over 6, I'll come to that. But use this idea. What I really wanted you to focus on is where this pattern comes from. On the inside, there's this crazy 1, 4, 2, 4, 1, 4, 1 kind of idea. And I didn't want you to just throw it up there and say, here, memorize this, 4s and 2s. It comes from a reason. It comes from a weighted average of trapezoids and midpoints. It's really easy to use. Let's just try, let's say we used n equal 4 on the cube problem above, okay? So the common notation then would be that you use something like S, capital S with a subscript of 4 to say I'm using Simpson's rule with 4 subintervals. And the first thing is the 1/3 and the delta x. The delta x is found the same way you always would find it, and that is the region, which is, I think we're going 0 to 4, is that right? Okay. Over how many subdivisions? In this case, 4. Now this will actually be like using a weighted average between the two of 2 rectangles or 2 trapezoids. But the delta x is 1. Inside is a single f at the left edge. So f at 0. Then 4 f's at the next point. If you started at 0 and delta x is 1, then the next one you come to is 1. Then 2 f at 2, then 4 f at 3, and a single f at 4. 1/3 out front. F at 0 is 0. 4 f at 1, 4. 2 f at 2, 16. 4 f at 3. So what's 3 cubed? times 4, 108, and f at 4, or 4 cubed, 64. 1/3 of, let's see, let's add that. 20 plus 108 is 128, plus 64 is 188, plus 4, 192, is what I got. Do you agree? And 192 divided by 3 is? 64, which is exactly what it truly is. Now, Simpson's rule is great, but it doesn't always come out exact. For cubes and below, it actually does come out exact. But for anything above, it's just a really, really strong estimator. Some cool things about Simpson's rule. First of all, Simpson's rule is perfect. Oh, would you write? I don't know if I pointed this out, but in this box here, this is important. Simpson's rule can only be used for even subdivisions. You can't use an odd subdivision, so you couldn't do S of 3 or S of 5 subdivisions, or 7 subdivisions. It's either got to be 2, 4, or 6, even only. Otherwise, the whole weighting idea falls apart. It actually can be, it's a really cool proof that besides this idea of midpoint trapezoid weighted average, it's also true that when you use Simpson's rule, it's like using area under parabolas. Simpson's rule is like using a parabola. So trying to make a parabola for this and then finding the area under that and then making a parabola for that. That's why it's so darn good for squares and cubes, because it is perfect. It's pretty cool. Let's go to one off the homework. Would you go to page 3, top of the page, 2C. Page 3, top of the page, 2C. I will let you use a calculator. C says find S4. You can do A and B, or you might have already done A and B, but do S4 part C. What is that? 4. Okay. Boom. So 1 divided by 12. F plus 4 plus 4 Did you get 3.14156? Wow, that's pretty crazy. What does it seem like? Yeah, why? It's the area under 1 over 1 plus x squared. What's the antiderivative of that? Inverse tangent, yes. Inverse tangent. Inverse tangent from 0 to 1, yes? Thank you. Is that right? Yes. Inverse tangent from 1 to 0 with the 4 out front. I forgot there's a 4 in the numerator, right? Okay? X from 0 to 1. That's 4. Inverse tangent of 1. Yeah, that should be fine, right? So, you don't even know what you just did, huh? Okay. So for thousands of years, how would you estimate pi? You would get out a string. You would draw a circle. You would measure the diameter. You measure the circumference, and then you divide. That's how you measure pi. That's where pi comes from. It's the ratio of circumference to diameter. And it wasn't very exact, as you might imagine. To be able to calculate pi, that's like a major step forward. This is one of millions of ways to calculate pi. And I just used 4 subintervals. And I was accurate out to the thousands. If I used 8 subintervals, who knows how accurate I could have been. And that wouldn't have been a big deal. So I know it's the end of the day and it's hard to get the ooh, but man, that's pretty ooh. Okay. You just estimated pi to the thousandth place. And no big deal. Okay, do you have any questions on last night's, or should we do another one on last night's before you just shut it down for 7 minutes, which is a waste of time? Let's do a swimming pool problem. Yeah, the kidney. Excellent. They asked about this also in the last class. Cool. Okay. Now, it says trapezoidal rule, but we could also use the average of the height rule, which is the same as trapezoids. Do you want to use trapezoid rule or average height rule? Okay, so for this first rectangle, it says these measurements were taken 2 meters apart. So the first rectangle is 2, and what's the average of the parallels in the first region? Now keep in mind that this distance is 0. So what's the average between the two? 0 and 6.2's average is 3.1. Okay? The next region is 2y. And what's halfway between 6.2 and 7.2? 0.5 from 6.2, so 6.7. What's halfway between 7.2 and 6.8? Are you adding these and dividing by 2? Please tell me you're not adding these and dividing by 2. What's the difference? Split the difference. Jesus, freaking Christ, are you kidding me? So 7? Wow, you are so calculator dependent. Your basic number sense is just obliterated. It's gone. That's so sad. I could ask a 4th grader what's halfway between 7.2 and 6.8, and they could answer quicker than you just did. Oh my goodness. That's ridiculous. What's halfway between 6.8 and 5.6? 6.2, that's better. Okay, what's halfway between 5.6 and 5? 5.3. What's halfway between 5 and 4.8? 4.9. And halfway between 4.8 and 4.8? 8. And what's halfway between 4.8 and 0? 2.4. All right, then. Should we? No, it's not. 2 times 3.1. 6.2. And then 2 times 6.7, 13.4, 14. 2 times 6.2, 12.4. 2 times 5.3, 10.6. 2 times 4.9, 9.8. 2 times 4.8, 9.6. And 2 times 2.4, 4.8. All right. So, taking the tenths, we got 14, 22, 28, 32, 36, 38, and a 3, 7, 16, 25, 27, 31, 34, 40, and a 4, 5, 6, 7, 8. I get 80.8. And what are the units on that? Meters squared. Okay. All right. 80.8 square meters. What else would you like to knock out that you either had a question on, we just didn't even do because you're a weasel? Let's see. Could we do maybe 1B? Yeah. Now that we've done 1, we could probably do 1A and B. So looking at that problem right beneath it, this is a conceptual problem. So you give it F. Does the table seem to indicate that F double is positive or negative? Negative? Why do you say negative? All right, perfect. I love it. If you look at second derivative, you're looking at the change in the change. And doesn't it go up by 1.6, then only up by 1.2, then only up by... So the change in the change is a decreasing or negative one. So it seems like F double seems negative because it's increasing at a decreasing rate. Right? Okay. Now, in terms of then the true area, we said the true area under F can be bound by midpoint and trapezoid if you know the concavity. So if this is concave down, we just said the second derivative is negative. If this is concave down, will trapezoids be over or under? Under, right? So trapezoids would be an underestimate of the true, and midpoints are above. So the trichotomy or three-part inequality would be the true area would be bound above and below by trapezoids and midpoints respectively. Are we good? Okay. Do we have time to do C or shut her down? Shut her down. Way to go, underachievers. All right. Have a lovely day.